So, good morning, everybody. Thank you so much for attending our last webinar from MOXXI group, working group. And today we have Seifeddine Jomaa. He will present the challenge in water monitoring and management in the Mediterranean. So first, I want to make a short presentation of our Dr. Seifeddine Jomaa. He's a senior scientist in the Helmholtz Centre of Environmental Research in Magdeburg, Germany. He holds a PhD in environmental engineering from the École Polytechnique Fédérale and Lausanne in Switzerland. His expertise lies in hydrology and water quality monitoring and modeling across the scales, with a particular focus on catchment-scale process. Dr. Jomaa research addressed the sustainable management of water resources, of mitigation of nutrient loss, and the integration of socio-economic and ecological assessment under the pressure of global change. He applies advanced modeling approach and monitoring techniques to better understand and manage complex human environmental interaction in water systems. He is author and co-author of more than 50 international papers, and now he lead and contribute in numerous European projects like Miracle Sustained Coast, InTheMED, GlobeWQ, WaterFARMING, and more. And currently, Dr. Jomaa is coordinating the OurMED PRIMA-funded project, aiming to promote sustainable and integrate water management strategies across the Mediterranean region. So, also, I want to give a small presentation about MOXXI working group. And we are under the International Association of Hydrological Science. Our mission is promote novel observational techniques to enhance understanding of the hydrological cycles. So our research are from multiple disciplines, trying to design, test, and share new technologies. So more than 150 scientists from more than 26 countries are in this group, and you are also invited to join us. We will share the link in the chat if you want to join and subscribe. So please, I want to give the word to Seifeddine and start with his presentation. Thank you so much.
Thank you, Jordi. Thank you all. So, first of all, I would like to thank Professor Manfreda for the nice opportunity to talk today on behalf of our OurMED team. Also, I would like to thank all participants for the time and attention to our talk today. So briefly, my name is Seifeddine Jomaa. I am a scientist at Helmholtz Centre for Environmental Research-UFZ, Germany. So today I would like to talk a little bit about challenges in water monitoring and management on the Mediterranean region and context. So this work mainly has been done as part of OurMED project. OurMED is a PRIMA-funded project by European Commission. We started in 2023, so we have 3 years duration project, and we will end next year in May 26. So the project is dedicated to the MED scale, which is clear and unique mosaic of environmental condition, landscape, climate circumstances, making or positioning the Mediterranean as a hotspot of species biodiversity. So the Mediterranean Sea is, I think globally is less than 3% of global ocean area, however, hosts more than 10% of marine biodiversity. This also has been recognized, I think, since our geological era. So it has been through different civilizations around the Mediterranean recognized as a hotspot of biodiversity, which resulting in one of the best food diet worldwide. However, agriculture became increasingly depending on irrigation, where 80% of farming system depends on irrigation. Also, the Mediterranean became a kind of hotspot of climate change, where is warming more than the global average. When we compare the average anomaly in terms of temperature on the Med region is higher than the global average. So the consequences or result, continuously we started observing all these kind of records. For instance, here in terms of wildfire extent and frequency around the Mediterranean, you can see the hotspot red location in terms of spatial extent in the recent years observed by Copernicus. But we can see also the dust due to the South country, North African desertification. We can see this kind of dust propagation from the North Africa to Central Europe, even North Europe, resulting in enriching snow, and we can see this kind of dusty rain everywhere, cars, which will result in more water consumption in the north in terms of cleaning of terraces, cars, etc. So we can see this kind of climate change, even though desertification in the north can result on water consumption, in the south can result in further water consumption in the north. So OurMED project came to tackle this kind of warmer climate condition and severe impact on water resources and water scarcity on the Med. And the idea to call for a transition from fragmented monosectoral water management to more equitable and multi-sectoral management, where we address simultaneously the needs of all users. However, considering the different water body capability in terms of groundwater, surface water, and reservoirs. You can see on the left-hand side here, we have this traditional water management, where traditionally water management has been tackled by sector. So we can see the upstream reservoir and domestic use. In the middle of the catchment, we have the more intensive agriculture and water authorities looking to secure more the agriculture sector, and the downstream, where we have the ecosystem services and functionality, and sometimes they are isolated and they don't have the minimum flow and the ecological flow for full ecosystem integrity and functioning. So our idea in OurMED project is to develop a comprehensive and multi-sectoral water management, where we leverage all our capability and the new advanced tools like modeling and sensor monitoring, but also earth observation, citizen science. All we can be integrated on digital twin system and simultaneously can deliver different support in terms of decision making for different stakeholders, which can be in terms of thematic maps, alarming, notification, risk mapping, and also positioning from the safe operating space. So to reach our goal, we are 15 partners from 10 countries: Germany, Spain, France, Greece, Italy, Jordan, Morocco, Portugal, Tunisia, and Turkey, with 4.4 million euro, 3 years duration of the project to reach our goals. You can see here our partnership are located around the Mediterranean, from the north to the south. Our partnership also including research institutions, but NGOs, SMEs, small medium-sized enterprises, where we can jointly, as an interdisciplinary team, we can jointly develop a sustainable solution, which they have higher probability to be implemented and taken by the local stakeholder and the local market. We need also demo site to test our solution and to design, co-design basically our methodology. So we have 8 demo sites around the Mediterranean region, covering different water-related problems, including water quantity, quality, sedimentation, eutrophication, seawater intrusion, biodiversity loss, groundwater overexploitation. So all together represent kind of a nice array of testing and demonstration laboratory, let's say, to develop and tailor our solution together with the local stakeholder and local needs. It's worth to mention here that the Mediterranean as a regional scale also has been considered as additional demo site, where mainly the water policy traditionally or commonly are designed to the national and regional scale. And our idea here to increase the science policy interface by including the regional scale. So we have 8 demo sites. 8 demo sites, but also we have 8 work packages, starting from the work management as work package 1. Work package 2, we have demonstration sites, characterization, but also additional monitoring. Work package 3 dedicated to the water governance and socio-economic assessment. Number 4 and 5 are dedicated to the modeling and the multi-objective water management and the NPS solution. Number 6 dedicated to the technology and how we can benefit from advanced technology towards sustainable water management. Number 7 dedicated to the upscaling and replicability, feasibility of our solution to larger and other demo sites. And number 8 dedicated to dissemination and communication of project result. Work package 1, classical work package where we ensure and establish collaborative environment and plan for regular communication and collaboration among the different partners of the project, but also we ensure smooth monitoring and delivery of our milestone and deliverable, and we organize all events related to the project, data management and risk management around the project. I will start with more details about the work package 2, which the demo site characterization and innovative monitoring around or among our demo site. So first of all, we started with system review and characterization of each demo site. However, also we based on this kind of first screening, we designed or we understand the additional monitoring needed to improve our monitoring strategy. Then this kind of monitoring has been tailored and coupled with the model needs and capability. So the idea to develop kind of monitoring can support the model calibration and validation, but also scenario design, and at the end synchronize or develop this kind of proper water management for multi-sectorial monitoring. Here I will show a little bit the use of high-frequency monitoring was proposed as one of the innovative solutions because we are like dealing with this rapidly changing environmental condition, and our graph sampling and biweekly, monthly water quality monitoring are not enough to capture the processes and the dynamical behavior of environmental condition. And here we are proposing the high frequency in Tunisia, for instance, and we have done this together with the local stakeholder where they shared with us their monitoring network, where they are monitoring continuously the discharge And together we optimized the location of two water quality catching stations within the measured river basin. The measured river basin is one of the strategic river basins in North Africa and Tunisia, more than 20,000 square kilometers, where 50% of the Tunisian population rely in terms of drinking water directly from this reservoir. So here the two catching station has been selected for this water quality monitoring, and the Sidi Salem reservoir here, the largest reservoir, and recently the water extent of the reservoir has been changed significantly to the extended drought in the region, and we have used the remote sensing here to detect the dynamical extent of water in the reservoir. Also, together with the ground observation, we developed kind of correlation between Earth observation retrieved water extent with the recorded ground observation volume of water stored within the reservoir. You can see the relationship here is not perfectly linear because we didn't consider the bathymetry and the change in the morphology in the region. However, here is clearly we can use Earth observation as a proxy for water volume and extent on the reservoir. Then the next step, we installed the two catching stations within the basin, and here two multi-parameter station with two nitrate has been installed in two locations, and the environmental condition also was not easy to install this kind of sensor, because we figured out that the river discharge within that basin is almost controlled by the upstream reservoirs in the region. Here you can see the sensor has been installed, and after a few weeks of installation, we found the sensor is fully of sediment and lacked of sediment. Here you can see the list of parameters has been measured by the Aquatrol sensor, but also we have used Trios, Nico, another sensor for nitrate concentration. Preliminary result observed here, but you can see we have a lot of gaps. We have a lot of kind of anomaly because we are still optimizing the installation of the two station, and we are developing kind of monitoring strategy, how to avoid all this kind of condition and stream flow regularity with our devices. Another also innovative monitoring approach we are developing under the supervision of Professor Salvador Manfreda from Federico II in Naples, where we are exploring the use of a camera system to detect turbidity, but also other water quality parameter. For instance, here the Bode River Basin has been used as an experimental site where we use artificial or natural clay kaolin as a tracer, where we can create a wave of turbidity within the river, but also in the downstream. We install different camera systems, the RGB multispectral and the drones, with all the needed setting in terms of panels, etc. You can see the river here before the experiment and during the experiment. And also we use a turbidimeter where they record real time, each 2 seconds, the turbidity. The results were very satisfactory when we compare the ground observation with the reflectance, the red reflectance of the RGB camera. And here we tested under different setting, this kind of camera system can detect properly the turbidity for a given circumstances, mainly when the turbidity is less than 200 NTU. Also, to give a context to this experiment, we have changed the hydrological setting. So we have done one experiment in the winter and another one in summer, but also we played a little bit on the peak of the turbidity. You can see here how the turbidimeter measures. So we have small peak and the second small peak and the higher one under different hydrological condition, and the camera, the multispectral, but also the RGB detect properly this kind of hydrographs, and the work has been nicely published as image processing for continuous river turbidity monitoring, full-scale test, and potential application in HAS journal. So the same experiment, also the idea to replicate it in Tunisia, however, we figure out we cannot do this kind of artificial clay as a tracer due to the high turbidity in Tunisia, but also the controlled upstream flow discharge. So with the local authority and the upstream dam regulation, we designed, or we co-designed one experiment together where they opened the gate for our experiment for a given time and given circumstances to create this kind of hydrograph where we can challenge our two-camera system and see how much they can detect the turbidity. So here the multispectral, here the RGB camera, and you can see the water level, but also the turbidity level before and during the hydrographs. So before the hydrographs reflected by this left panel, you can see the water level was less than almost half a meter, and the turbidity also less than 100 NTU. And during the experiment, we reached more than 2 meter water level, and the turbidity more than 500 NTU. So Domenico, our colleagues in Napoli, exploring the results of this experiment, where you can see here, for example, the different time spot, like 11 when we started the experiment, and here at 1 o'clock, here at 3, and here at 5 o'clock the afternoon. So you can see the increase of discharge and turbidity, but also you can see the reflectance and the impact of the shadow and all this boundary condition which can impact our result. So Domenico did all this image processing and working on this, and the preliminary result showed that the RGB camera, so he analyzed only the RGB camera, so clearly we can see the increase of the hydrographs. However, during the peak, it seems we have a kind of saturation, and we cannot, so the RGB camera cannot see the peak down or the recession properly. So so it seems no influence of turbidity on the RGB band pixel intensity. So here in the black, we can see the sensor monitoring and the RGB camera different reflectance show that not nicely the peak. So the recession, they miss a little bit the recession. Our hypothesis may be above 200 NTU. It seems the RGB camera has some limitation, and we are exploring now the multispectral camera system. So here, Professor Manfreda developing with his team very comprehensive research framework how to monitor water quality from the camera system. So the next work package, because mainly my talk is about monitoring and management, but the monitoring and water management, they cannot be optimized if we don't know the governance and the expectation from the different stakeholders. And here work package 3 was dedicated to that explicitly. So how we can understand the water governance and the different system, how we can create this kind of long-lasting space, learning space, and co-design of solution and implementation. Also, how we can promote innovative approaches for conflict mediation in water-related issues. To do so, in all our demo sites, the 8 demo sites, we establish different living labs, and all these different living labs, they have been animated through stakeholder workshops where we meet. They have been divided in 3 sections, so problem definition, co-design of solution, and the third one will be testing of the solution proposed by stakeholder using our modeling framework and project methodology. So here you can see this kind of meetings has been organized on all our demo site, where we try to identify problem together, but also disentangle their priority, but also interest in changing condition or adopting like new technology and new, maybe more tailored solution. For instance, here in the Konya closed basin in Turkey, you can see the mapping of the different stakeholders in terms of social capital, economical capital, and human capital. So always all stakeholder has been ranked in that, because all this kind of mapping is crucial to determine this kind of diagram, where we can evaluate the power, but also the interest of all stakeholder part of that exercise. And later on, we can tailor, or we can understand how the decisions are taken within the system. Also, system thinking and modeling is part of our innovation in OurMED project, where also we try to understand the perception of stakeholder in terms of future adaptation strategy. Because we figure out in terms of future projection, usually we give more weight to the climate forcing and the climate as a driver, but we neglect a little bit the human behavior and the human adaptation part. And here our team in Turkey, they are expert on that, and they are using kind of still a software where they try to create kind of causality between surface water, land use, crop yield, groundwater, in terms of behavior among the different stakeholders. To do so, here we need to couple different model, like deterministic process-based with social science model, all coupled together in order to develop this kind of causality framework in our demo site. Usually when we do this exercise, we use monetary indicator like crop profitability, etc. But also we know for the ecosystem part, so sometimes we need to use the non-monetary indicator as human well-being. And here, for instance, we have used the nature contribution to people. We following the 18 indicator of the IBBS reporting and framework, and all our demo site has been evaluated in terms of nature contribution to people. Either they have been deteriorated in the recent years, improved, or no change. So the next work package was dedicated to the co-design of multi-sectoral solution, because this equitable and multi-sectoral water management also require more multi-sectoral modeling and more multi-objective function to allocate enough water in good quality for all stakeholders. So we have dedicated a specific work package on that, where we try to understand pathways toward multi-sectoral water management for each demo site among the different sectors. Then we have to assemble the right model portfolio aligned with the stakeholder needs and demo site requirement, and test them based on the future projection. Then later we can evaluate this kind of scenario, which are suggested by stakeholder to improve the current situation. To do so, we worked a lot on the integration. We call it integrated management. So how we can integrate all water capability in terms of surface water, groundwater, but also to fit the requirement of different users in terms of social, economic, political, ecological, and climate. To this end, we need to develop variables and constraint and an optimization method. For each demo site, we did this kind of methodology for multi-objective water management, where we try to understand the objective function, the constraint, and the decision variable. And based on that, we can select the most appropriate modeling portfolio. For instance, here for the Bode River Basin, we did surface water coupled with groundwater. So we have discharge nitrate coupled with mud flow. Then simultaneously, we have three output of our model. So we have discharge nitrate concentration with the river and the groundwater level on the system. But this is not enough for the ecological part. So for the ecological part, we need additional parameter, which can be water temperature and dissolved oxygen. Then our deterministic model are not suitable for that. So then we used AI-driven model to complete those two parameters. And with this 5 output, we can ensure that all stakeholders, they are well represented on that. And here we can see the type of outputs. So simultaneously, all other demo sites, they have used a portfolio of different model, coupled and assembled with different type of outputs to satisfy the different user. So Albufeira system, which our Spanish demo site was unique on that direction, because Albufeira is very important in terms of rice production in Valencia, around Valencia, but also is a Ramsar site, which the lake, the Albufeira lake, in one hand absorb all floods on the surrounding Valencia city, but also ensure enough water for migratory bird in the summer period, as you can see. The Albufeira system, if we see groundwater nitrate concentration, historically is hypertrophic condition. So nitrate concentration in average about 250 milligram per liter above than the 50 milligram per liter allowed. But within the lake, also profile A is too high, and above, you can see here above the threshold, which is 90 microgram per liter. When we started the project in June 23, in October 23, the lake has observed a sudden brownification problem due to the minimum flow. So in very sudden period, the water dropped down to less than 25 centimeter, impacting the whole lake system. And our colleagues in Spain, they are working on this issue by the constructed wetlands system. So they are proposing the constructed wetlands as mitigation option around the lake, where they have a constructed wetlands and they are monitoring the efficiency of that system before the wetlands and also they are monitoring nitrogen concentration at the outlet, but also a little bit downstream before reaching the Albufeira lake. So this is the 3 locations where they are measuring nitrate concentration to prove the efficiency of this kind of constructed wetlands. And you can see the nitrate concentration in the green spot much lower than the entering, so almost less than the half of the inlet of the wetlands. However, and the idea of our team in Spain to replicate this kind of constructed wetlands elsewhere and to tailor it to the different circumstances. However, the flood of 2024 in Valencia has mixed a little bit the perception and the priority among the stakeholders. So first of all, we lost a lot of kind of monitoring devices during the flood, but also flood became a priority compared to water quality. And stakeholder, they are more interested now to reactivate flood control and flood risk management plan, which has been proposed a few years ago, but they didn't implement them due to the cost. But the event of 24 showed that mitigation option costs are much less than the damage and the impact of this one single flood can happen in the region. And we are trying to use the same perception now to tell them also water quality is the same. So this investment around this kind of constructed wetlands maybe for the long term and the multi-benefit aspect of constructed wetlands, also very profitable. So to summarize this, so the Albufera system, now they are shift to very comprehensive modeling and water allocation tools, so Aqua tool, where they put all kind of interaction and causality in the system. But the good thing, this tool has been co-designed with EPV, our scientific partner with the water authority. So they are using the same model to do this kind of exercise. Also, climate projection is part of work package 4, where we test our scenario under current and future projection, but also we are considering the near term, where we are exploring weather forecasting capability from different European and then national institution to get the climate forcing for the next few days, months, to develop this forecasting capability in our digital twin system. So work package 5 is about NBS. So we are also working on the development of NBS. So based on lecture review, we figured out NBS became one of the cost effective mitigation option with different societal benefit. And NBS not implemented, as we can see in this diagram, is not implemented on biodiversity and ecosystem related, but also implemented in flood control, water quality, but also human health and soil protection. Together with our colleagues in Napoli, where they are leading this work package, they are trying to develop kind of methodology and modeling framework where we can use the catchment characteristics and the preliminary information from stakeholder together with a decision matrix to develop kind of preliminary NBS cartography and catalog where we can share it with stakeholders to accelerate the dialogue and engagement, but also to receive feedback from them to better optimize our NBS cataloging and mitigation option. Here, 2 examples on the Boda River Basin and Konya in Turkey, and we have done this similar exercise with all demo sites shared with stakeholders. And we started receiving feedbacks. For example, here in Turkey, we receive feedback mainly about the spatial resolution. So stakeholders, they think our large scale and regional data is not enough for their local scale implementation. They think also maybe we can or our framework can not consider specific small problem like wind magnitude and direction, like wind direction and magnitude, which are crucial for their Konya system farming. But also mainly about the input data, because now when we develop this kind of framework, the idea to use open access, open source data, but later can be tailored to the demo site needs. We are working together on this kind of feedbacks, and our idea now how we can consider the feedback, integrate them in our system, and maybe offer them maybe another more tailored solution and catalog. We figure out also the NBS, when we did it, we are considering the landscape context mainly, together a little bit with the co-design stakeholder, but neglecting a little bit the NBS impact, the business model, and monitoring and evaluation. And we are proposing within the project as a holistic framework where the NBS is not kind of tailored to the catchment characteristics and maybe stakeholder, but also it should be considered in terms of business and implementation, feasibility, and how we monitor and evaluate it after the full implementation. So we are proposing kind of a holistic framework of NBS where all the steps should be considered at early stage to ensure full uptake of NBS solution. So work package 6 is about technology, so how we can benefit from increasingly emerging technology and advanced technologies such as Earth observation, but also smartphone apps tailored or using real-time Earth observation data to give kind of notification and aided decision evidence. But also digital twin also has been proposed as another tool where we can be considered as the next generation of DSS tool. So for the smart AG or smart application, smart agriculture application, they can integrate Sentinel-1, Sentinel-2, and Galilei, openly available data to the cropping system of the farmer, where they can receive daily report. Also, they can have historical data in terms of DVI, but also in terms of other parameters, where they can see any deviation or anomaly on their irrigation system or on their cropping system, where probably they can take early decision to attenuate the climate related impact. For instance, here our application has been tested on the brownification of the Albufera system, which happened in October, November, exactly October, November 23. So here we can see the image in September and the image in December. So this kind of color show clean and deep water, and suddenly in 2 months, the color of the lake and the level of the water in the lake dropped down, reflecting high chlorophyll A on the lake. Other Earth observation products use it in terms of wetland use intensity. So here we offered also for the Albufera Lake this kind of wetland intensity. In the Arborea in Italy also we have offered them this kind of capability. In terms of deforestation and forest type in Germany, here we have animation where you can see it's not working properly, but we lost almost 70% of the forest on the Harz during 5 years. And here you can see all the area, deforested area, let's say on the Harz mountain on the last period. But also our colleagues, RSS in Germany, partner in our project, they developed this vitality trend where they figure out that almost the 24, 23, so this deforestation stopped, and we have reforestation of the system. So the digital twin has been proposed also as another innovative and next generation of DSS or decision support system, where we integrate model with data, with decision forecasting capability to give timely and real time kind of status of our catchment and different parameters, but also the forecasting capability, where we integrate model with different climate forcing data, and we can give model result. So the Bode River Basin in Germany has been selected as one of the best demo sites to develop this technology because we have enough data. One of the best monitored river basin. Our model are advanced because we have surface water, groundwater, but ecological model. We have good engagement with stakeholders. We have scientific knowledge developed based on the at least 15 years of monitoring and continuous interaction with stakeholders. And the experience of drought also can be used as a boundary condition, as a natural scenario of climate change, where we can define our ecological boundary condition. So here, all the data we have, and the different model has been coupled, as I mentioned, like ammonium nitrate with mode flow with data-driven model. So all coupled to have a different output. So here I will end my talk by showing you our model results. So we are, you can see in terms of discharge, our model. So here the result by September 25. So our model almost daily. So we like timely can be updated by 2 days. So each day can the model be extended based on the available climate data. So it has been tested in different catching stations. And you can see the accuracy, this task for the outlet of the catchment, here Silberhütte. So without the new calibration. So the model has been calibrated, I think, 2015 until 2018, because this period where the deforestation started. So we have selected this period here to calibrate the model under this transition part. Then we have run the model for the whole period. And the model give a very good result in terms of discharge, but also in terms of nitrate and concentration. Here, discharge still, you can see all this catching station, and the nitrate concentration here. You can see the nitrate concentration. So the model can mimic also the dynamical changes. Here, the sensor data are not retrieved from the from our server yet. So we have the data, but it's not synchronized with our model. Again, also here is not synchronized. You can see also we have some outliers. So there is some. So the in-situ data still can be cleaned. So there is some data here which we believe we have enough evidence that this kind of dots here are completely wrong. And usually due to our maintenance, when we go to the field and we clean the data, so the sensor stay recording, but wrong value because it's out of the water. You can see here during the deforestation in Silberhütte, this station very close to the Harz, during the deforestation period, we have higher nitrate concentration exiting the Harz mountain due to the loss of the forest uptake. So we don't have forest and we don't have nitrate uptake, so we have more leaching. So, and it was a nice exercise to test the model, if the model can mimic this. In Silberhütte, it seems to some extent we detected, but little bit downstream in Maisdorf, you can see here, the model missed that, which was not also pronounced in the former period of our calibration. So again, in the house Neindorf, a little bit downstream, more downstream, so the model also could not detect that properly. But this we will include it on the next step. Also, this my final slide is about the capability of this kind of grid-based modeling. So we can have this kind of thematic maps where we can observe. I'm sorry about this animation, but we can observe continuously the changes in the catchment grid-based one. Okay, thank you. So I will stop here and I'm happy to answer your question. Thank you.
Thank you so much, Seifeddine. So feel free, please, to ask everything. So till now, we have 2 questions from Marvin Tejada. He has, can we use the application free and open source? I mean, he referred to the mobile application.
Good question. I think this one is Agro Insider. So our colleagues in Spain and Portugal, Agro Insider, are developing this kind of app. And they are SME, like private sector. And I think they have it, I think freely application can be tailored to demo site, but it should be very restricted for a given period, given crop type, because they are kind of selling this kind of service and product. So they have some demo for free, but I think the full, let's say, version should be paid, so it's not open access. Because the idea of the project to work together with stakeholders and SMEs and make the connection maybe between the private sector and the potential maybe user and customer. And this one of the idea of this kind of app. So the digital twin developed by Idrica in Spain, and the smart AG developed by Agro Insider in Portugal.
Okay, thank you. So in my case, I have a question, like PhD students and maybe young scientists. One of the most challenging is the monitoring and the keep constant monitoring in the future. So in your experience, how we can push, in this case, administrations, companies, or politicians to invest more in monitoring, I don't know, to acquire more data for improve our model like digital twins?
Yeah, I think good question and not easy to answer, but I think because monitoring, we have two maybe strategy, let's say, of ground observation. So we have this long-term grab sampling. So I think the water authority, they are really good on long-term and grab sampling, like monthly, means for discharge, I guess daily, they are continuously monitoring. I'm talking about water quality. Usually they monitor it each, either bi-weekly or monthly. But for them, the long-term perspective is very important. However, also the other strategy to increase the frequency, the time frequency of the monitoring, so to have hourly or sub-hourly monitoring, which mainly you need a sensor, and usually these kind of sensors are expensive, but also needs a lot of maintenance. And many water authority, they shift to this kind of innovative high frequency monitoring, but usually they cannot put it everywhere. So they can spread it in a strategic catching station where they can monitor better. I think for our models, we need both. And for our model and physical understanding, we need kind of balance between long-term, because the long-term also needed for trend analysis and shift in the hydrological and environmental regime. But the high frequency also needed to understand the daily fluctuation, seasonal one. Also, for example, the good example I have shown is about the upstream deforestation, how the upstream deforestation impacted the downstream nitrate gauging station. And immediately we recognize this additional or increase in leaching, which mainly due to the forest die back. But also the question how long this increase in leaching will maintain. So according to other demo sites in Bavaria, for instance, where they experienced this kind of deforestation a little bit earlier than us, so only a few years we expect this high increase, then they come back again to kind of steady state, other level of nitrate. So Earth observation also became a very powerful tool for monitoring also. Again, we know the limitation of the spatial scale, sometimes also the limitation on the cloud. But I think to conclude, I think we need the three approaches: long-term grab sampling for trend analysis, high frequency a strategic gauging station to understand processes and dynamics, and Earth observation also, and citizen science, what Salvador are doing also needed. So we have to explore. Also at UFZ, we have a team working on this NLP, like large language model, like text mining. So they try to retrieve also data from newspaper and text, which I think in the future will be also a big source of information.
Okay, interesting. So if we don't have more questions, maybe we can proceed to conclude this webinar. So thank you so much, Seifeddine, for this amazing presentation. Thank you so much, everyone. So we can close here. I don't know if Professor Salvador Manfreda want to share some words.
Thank you, Seifeddine, for this beautiful introduction about the issues that Mediterranean environments are facing in a changing environment that is not only related to climate, but also to other factors that are posing under pressure water resources. The discussion was very stimulating, and we received a lot of registration. I'm very happy about this initiative, and now is managed by the group of young scientists that is coordinating the initiative. I would thank all of them for their enthusiasm and passion in leading this dissemination initiative. I would also thank all the participants for joining us, and take the opportunity to remind all of you that we have a dedicated web page for the MOXXI working group. Now we have more than 200 registered participants, and we have also dedicated the YouTube channel where all these webinars will be recorded and posted. Thank you so much.
Thank you, Prof.
Thank you. Thank you all. Thank you for the opportunity, and have a nice day. Bye-bye.
Have a nice day. Thank you.